Chapter 19, Ionic Equilibria in Aqueous Systems. In this chapter, we're going to learn buffer solutions. What is a buffer? How to calculate the pH of a buffer, and the Henderson-Hasselbalch equation. The titration curves for acids and bases. Slightly soluble ionic compounds, QSP, KSP, and solubility. Equilibria involving complex ions. An acid-base buffer is a solution that lessens the impact of pH from the addition of acid or base. An acid-base buffer usually consists of a conjugate acid-base pair, where both species are present in appreciable quantity in solution. An example is acetic acid combined with a similar amount of sodium acetate. Okay, so this is a salt. The acetate is the anion of this acid, and this is weak acid. Okay, and this is a conjugate base. All right, now what if we combine strong acid and its conjugate base would be chloride, for example, sodium chloride? Okay, now the problem is for strong acid, it will completely dissociate and becomes chloride ion. In solution, there's no hydrochloric acid exists because they 100% dissociate. And therefore, in order to have appreciable quantity of conjugate acid and base together, then we have to use weak acid. Okay, weak acid and conjugate base have equilibrium. So an acid-base buffer must be solution of weak acid and its conjugate base, or weak base and its conjugate acid. This diagram shows the effect of adding acid or base to an unbuffered solution. So on the left side, we show a solution made of hydrochloric acid. Okay, so we adjust the concentration until pH becomes 5. Okay, now we add more hydrochloric acid into this solution. What do you expect to change? When hydrochloric is added, hydronium ion will increase, and that will decrease the pH value. 1 milliliter of hydrochloric acid will change pH value from 5 to 2. Okay, now what if instead of more hydrochloric acid, we add sodium hydroxide? The sodium hydroxide will react with hydronium ion in the solution to increase OH hydroxide concentration, and that will increase pH. 1 milliliter of sodium hydroxide will increase pH from 5 to 12. The conclusion is that without buffer, the solution pH changes dramatically when you add a tiny amount of strong acid or strong base. This diagram shows the effect of adding acid or base to a buffered solution. We make a buffer solution by mixing 1 molarity of a weak acid, and that's acetic acid, with 1 molarity of its conjugate base, and that is sodium acetate. The pH of this buffer solution is 5. Okay, so pH is the same as the one we made in the last slide, but this time solution is a buffer solution. So if we add 1 molarity of hydrochloric acid into this buffer solution, what do you expect to see? Okay, what you see is the pH value change very little, from 5 to 4.98. What if we add hydroxide, sodium hydroxide? Same amount, 1 milliliter, all right, and the pH value increased from 5 to 5.02. So in either case, the pH value changed very little compared to the other slides where we add acid base to a solution without buffer. Okay, so the conclusion is buffer lessens the impact from adding acid or base. In order to understand how buffer works, first we need to explain common ion effect. Let's use acetic acid as an example. Acetic acid dissolves in water and dissociates slightly to produce acetate ion. Here is the dissociation reaction. Acetic acid combined with water give you conjugate base, which is acetate anion plus hydronium ion. And this reaction goes only slightly towards the product because it's a weak acid. Ka is a small number. Okay. Now, what happens if we add sodium acetate? Now, sodium acetate is a salt that will completely dissociate, becomes two ions. One is sodium ion, one is acetate anion. Okay, so essentially we are adding associated anion to the solution. And note that the acetate anion, there's already some generated by acetic acid. So this anion is called a common ion because it belongs to sodium acetate and also acetic acid. So both of them contains this anion. So it's called a common ion. Whenever you add this anion to the solution, you're adding a product to this dissociation reaction. According to Le Chatelier principle, this reaction will favor reverse reaction. Okay, and that means it will reduce the percent of dissociation of the acid. Okay, and therefore the pH value of this solution will change according to the relative concentration of this acetic acid and sodium acetate. This table shows the effect of added acetate ion on the dissociation of acetic acid. With pure acetic acid, no acetate anion added, the dissociation percentage is 1.3%, and this is a weak acid, which generate hydronium ion 10 to the minus 3, pH value 2.89. When a small amount of acetate anion is added, the dissociation percentage goes down, decrease. As we explained in the last slide, this is a common ion. When this common ion is added as a product, the dissociation reaction goes reverse, and which reduce the percent dissociation. Okay, the hydronium ion decrease and pH increase. Okay, and the more acetate anion you add, okay, the smaller the percent dissociation of the acid. Hydronium ion decrease, pH increase. Okay, in fact, this is the buffer solution because it has a weak acid and also a conjugate base, and you can see the pH is relatively stable around this solution. So how does a buffer work? Well, let's use acetic acid and acetate anion as an example. The buffer solution must contain appreciable amount of this acid, weak acid, and conjugate base. So let's assume we have 0.5 molarity of this acid and 0.5 molarity of acetate anion. Okay, A minus represents this anion. And in the solution, there's a equilibrium between these two substances described by this equation. Okay, the pH value of this solution is determined by the relative number of this acid and its conjugate base. In fact, we'll show you an equation that pH value is determined by the ratio of Ha and A minus. Okay, the acid and the conjugate base. It's the ratio that determines the pH value. Now, suppose we add a small amount of hydronium ion into the solution. Okay, so let's say you have 0.01 molarity, okay, hydronium ion. Now, even though this is a small amount of hydronium ion, if you add to a non-buffer solution, all right, the pH value will change greatly. Okay, we can calculate pH equals negative log hydronium ion, which is 0.01, and that gives you 2. Okay, so if the solution was neutral, 7 goes 2, that's a big change. Even if the solution is not neutral, let's say weakly acidic, let's say 5, okay, a pH 5 goes 2, is still a big change. So a small acid added to a non-buffered solution will give you a big pH change. But if we add this to this buffer solution, acetic acid and the anion, what happens? Well, notice that in this solution we have an acid. We also have a base. Base is the conjugate base, is the anion. This base will react with hydronium ion. Okay, so what happens is the hydronium ion react with acetate anion, which is the conjugate base, to generate the acid, the acetic acid. So this will, the base will decrease a little bit, and the acid will increase a little bit. Because in the solution we have large amount of the base, we add a small amount of hydronium ion, so the change is very little. And similarly, the acid also change a small amount. The ratio, okay, doesn't change much, and the pH remains almost constant. Okay, a little change. Okay, similarly, if we add hydroxide, again, even a small amount, 0.01 molarity, will give you a big change if this is added to a non-buffer solution. But if you add to this solution, then notice we have acid in the solution. So the hydroxide will react with this acid. Okay, it will react with acetic acid to form the acetate anion. So again, in this case, the acetic acid decrease a small amount, the conjugate base increase a small amount, and the change is very small because 0.5 compared to 0.01, and the ratio doesn't change much again, and pH remains almost constant. Okay, so a buffer works because a large amount of acid, okay, in this case is this acetic acid, can consume the small amount of added hydroxide. So you add a small amount of hydroxide, but the small hydroxide will react with acid. Or the large amount of basic component, that's this one, acetate anion, will consume the small amount of hydronium ion added to the solution. In other words, the buffer solution will absorb the added hydroxide or hydronium ion and maintains pH value constant. So how do we calculate the hydronium ion in a buffer solution? Again, we show this equation, the equilibrium between the weak acid and the conjugate base. And the acid constant Ka for this weak acid is the product divided by reactants. Here is the base, okay, times hydronium ion. So hydronium ion is here, divided by the acid concentration. And in order to calculate the hydronium ion, we need to modify this equation. So acid concentration goes to the left side, you need to multiply by it. So if you divide by a number on the right side, when you move to the left side, you need to multiply. And this one you need to divide. Okay, so the base multiplication in the right side, if you move to the left side, you need to divide by it. So here is the concentration of hydronium ion, which is Ka, times the base. So you see the base becomes denominator, and acid concentration becomes numerator. Okay, so that indicates that the hydronium ion concentration is a constant Ka. Ka is a constant times the ratio of the acid divided by the base. Okay, so the Ka is constant, so hydronium ion depends on the ratio of the buffer component concentration. Now, if this ratio increase, if acid increase, then hydronium ion increase, of course. If the ratio decrease, means acid concentration becomes smaller, then the proton hydronium concentration decrease. Suppose we have a buffer solution with equal amount of acid and conjugate base. For example, 0.5 molarity acid, 0.5 molarity of conjugate base. And at the molecular level, you can see they have equal amount acid and base. So acid in this case is 4, and the base also 4 if you count the molecules. Now, if we add small amount of hydronium ion into the solution, what happens is the hydronium ion will react with this base, okay, to form the acid. So in this diagram on the bottom, you will see the base decrease a little bit here, and the acid increase a little bit. And at the molecular level, if you count, the acid becomes 5 increase, and the base becomes 3. All right. Now, remember in the last slide, we showed the hydronium ion in buffer solution is determined by the ratio. So if you look at the ratio, it doesn't change much. Okay, the relative number, okay, change very little, even though the base react with hydronium ion decrease small amount, and acid increase small amount, but the ratio doesn't change much. So hydronium ion concentration does not change much. Similarly, if we will add a hydroxide, the hydroxide will react with acid, okay, react with acid. So now in this molecular level, if you count, the acid becomes only 3, but the base becomes 5. Now if you look at the bottom one, the acid decreases slightly, the base increases slightly. The ratio doesn't change much, and therefore the hydronium ion doesn't change much, and the pH remains constant. In sample problem 19.1, we'll study quantitatively how much pH change for a buffer solution when hydronium ion, hydroxide ion are added. The buffer solution is made of 0.5 molarity of weak acid, hypochlorous acid, and 0.6 molarity of the conjugate base, sodium hypochlorite. And first we calculate the pH of this buffer solution. And then we add a small amount of sodium hydroxide into the solution, and then calculate the new pH value. And finally, we add a small amount of hydrochloric acid, okay, and then calculate the pH and see how much it changes. So our plan is we use the given concentration to calculate first the initial values, okay. And remember, it's a weak acid base, so in order to calculate hydronium ion, we have to write the reaction, set up a reaction table, solve X. Okay, so that's for A, and for B, we assume because sodium hydroxide is a small amount compared to the acid in the buffer solution. So buffer is 0.5 molarity. The base will react, so we assume all the base sodium hydroxides react with the acid consumed. Okay, in C we assume all hydrogen chloride are reacted by the base in the solution. Okay, and then we set up the so after reaction we calculate the new initial concentration, initial value, and set up the table and calculate the hydrogen concentration in the solution. Let's first calculate the pH value for the buffer solution. And we first write the reaction equation between the weak acid and the conjugate base. And this is the weak acid dissociation reaction. Okay, so as usual, we list the table, and the initial concentration are given, the weak acid, the conjugate base concentrations, the change, equilibrium, all right, initial minus for reactants, initial plus for the product. Okay, to calculate X, we notice that Ka is given, so we write Ka is the product divided by reactants, but we assume X is a very small number. This is due to the small K acid constant. Ka is very small, and therefore 0.6 plus X is approximate to be just 0.6, and 0.5 minus X is approximate just 0.5, and this make a solution much simpler. So X can be easily solved, and you can see X is the hydronium ion, which is calculated by Ka, and so that's the Ka multiplied by the 0.5 is the initial concentration of the acid and the initial concentration of the base. So again, we see the hydronium ion concentration is determined by the ratio of the acid over the base. Okay, so if the Ka is very small, okay, very small as in this case, then the hydronium ion is only determined by the initial concentration. Notice that we don't even include the X, the change, just initial. So that's a approximation which is valid when Ka is very small. Otherwise, you need to 0.5 needs to be minus X, and 0.6 needs to be plus X to calculate hydronium ion. Okay, but here X is very small, so just initial ratio of acid over base. Okay, and the calculate hydronium ion, we can calculate pH, but first we check it's a small number. Okay, the ratio to the initial concentration is very small, so assumption is justified. So pH is negative log hydronium ion, in this case give you 7.62. So this is the pH for the buffer solution made up of 0.5 molarity of weak acid, 0.6 molarity of this conjugate base, without adding hydronium ion, hydroxide ion. So next we're going to add the acid or base to see how change compared to this number. Now let's look at B. We add 0.02 moles of sodium hydroxide to 1 liter of buffer solution. And we know that when sodium hydroxide is added, it will react with the weak acid, and that will change the initial concentration of the acid. And therefore, the pH of the buffer solution may change. So in order to calculate the new initial concentration of the weak acid, we need to know the concentration of hydroxide added. Here, 0.02 is the number of moles. So we need to calculate the concentration, which is number of moles divided by volume, and that gives you 0.02 molarity. So this is the concentration of hydroxide added to the buffer solution. And because the concentration of the weak acid is 0.5, which is much larger than 0.02, so we can assume all hydroxide is reacted, consumed, and the acid left will be 0.5 minus 0.02, give you 0.48. So this should be the molarity of the weak acid left after the acid-base reaction with hydroxide. But also notice that when the weak acid react with hydroxide, it will produce this conjugate base. So this will increase. Increase should be the same amount of the hydroxide added. And so it should be 0.6 plus 0.02, give you 0.62. So that's the new concentration of the conjugate base in the buffer solution. Okay, now we do this calculation because the reaction is a simple acid-base reaction, 1-to-1 ratio. But there's a formal way to do this calculation, and that is we write the acid, weak acid plus hydroxide. Okay, so that's the acid-base neutralization when you add hydroxide, which give you water and the conjugate base. And we also draw the reaction table. The initial acid is 0.5, the conjugate base is 0.6, and we add 0.02 base hydroxide added. 0.02 hydroxide is in small amount, and the acid is in excess amount, and therefore the reaction change should equal to the hydroxide, because that's a small amount. All of them will be reacted, and the same is for acid. So change and which produce also same amount of the base or the anion. And so the final concentration after this neutralization give you acid 0.48, which equal to the one we calculated before. And the conjugate base anion 0.62 also equal to this one. Okay, so you see in sometimes if the acid-base reaction when you add hydroxide react with acid is simple, then you may not need this table. Okay, but writing the table make it clear. Okay, and avoid mistakes. So it's preferred. All right, and also notice that these two 0.48. Okay, this one 0.48, 0.62. These are the new initial concentration of the acid and the conjugate base in the buffer solution. Okay, in order to calculate the hydrogen ion in the buffer solution, we need to use this as initial concentration and write the reaction table of the weak acid dissociation reaction, and then solve X just as we did before, and calculate hydrogen ion and then calculate the pH for this buffer solution after hydroxide is added. With the new initial concentration added, now we write the equation again, the acid, water, conjugate base, and hydrogen ion. So this is the acid dissociation reaction, and we draw the reaction table in the new initial concentration for the acid, new initial concentration for the base. We write the change, equilibrium, and we solve X. So to solve X, we use the equation of Ka equals product divided by reactants, and we should get the same equation, and that is hydrogen ion concentration equals Ka times the ratio of the acid divided by the base. Okay, so you have seen this equation several times for weak acid, the acid-base buffer solution. The hydrogen ion concentration is determined by the ratio of the acid divided by the base. Now, if Ka is small, as in this case, X will be very small. So the acid concentration in equilibrium is approximated by the initial concentration, and the same is the base. So just use initial concentration, and we get the hydronium ion in this buffer solution after hydroxide is added. And the new pH value can be calculated to be 7.66 compared to 7.62 in the buffer without before hydroxide is added. The addition of small amount of base caused pH to rise only very slightly from 7.62 to 7.66. Now let's look at the C. Adding 30 ml of 1.5 molarity hydrochloric acid to 0.5 liter of the buffer solution. Now in B, we add solid sodium hydroxide. Here, hydrochloric acid is a liquid with a certain volume. And this makes it more complicated because now the initial acid and the conjugate base in the buffer solution concentration will change not only because you add hydrochloric acid reactions, but also due to the volume change. Because liquid changes the total volume, so the concentration will change. Okay, so first we are going to calculate the concentration of the initial concentration of the acid base due to the volume change, and then we calculate the change due to the neutralization reaction when hydrochloric acid is added. Okay, so to calculate the new concentration, okay, we calculate the new volume. All right, so the new volume is the volume of the buffer solution plus the volume of the hydrochloric acid added, and this is the total volume. Okay, so that's the total new volume, and the concentration of the acid, all right, is the concentration, initial concentration before you add hydrochloric acid. You times the molarity. Okay, molarity times volume. That gives you number of moles of the acid. Okay, so that's the number of moles in the solution divided by the new volume. Okay, that gives you the new concentration due to the volume change. Similarly, we can calculate the concentration of the conjugate base, sodium perchloride, which again you calculate number of moles divided by new volume, that is the concentration, and then hydronium ion concentration added. You need to also calculate the concentration by the number of moles divided by volume. Okay, so molarity times volume, that's the constant number of moles divided by new volume, give you 0.085. So now we have the new concentration of acid, conjugate base, and we have hydronium ion concentration added. We know this hydronium ion will react with the with the base. This is the base. So these two will react, and that will change the initial concentration. So we write a reaction between these two. So this is the base, and this is hydronium ion. Okay, when you add to it, it will neutralize it. Okay, forms water, and the base becomes conjugate acid. Okay, so we can, just like before, we draw the table and initial concentration. So this is the concentration of the base due to the volume change. Okay, after volume change, and this is the acid after volume change, and this is the hydronium concentration added. Again, this is a small number. This is in excess amount, so the change will be same as the hydronium ion concentration, and the same amount produced for the product, and the final will be for the acid base will be 0.48, for acid will be 0.56. So initial plus the change. Okay, so now with the new initial concentration of the acid and the conjugate base calculated, we write the acid dissociation reaction again and draw the reaction table in order to solve the new hydronium concentration. Okay, so the change, the equilibrium concentration as usual, and to solve X we use Ka, and we should get the same equation, and that is hydronium ion concentration is Ka multiplied by the ratio of the acid divided by the base. And because X is very small, so the acid concentration is just initial acid concentration, which is 0.56. Because X is so small, it can be omitted. Same as base, 0.48 is here, and that gives you 3.4 times 10 to the minus 8. We calculate the pH, 7.47. Again, we show that addition of a strong acid lower pH only slightly, from 7.62 to 7.47. Here's a summary of the sample problem 19.1. We start with a buffer solution with acid and conjugate base concentrations given, and the pH value is determined by the ratio of this acid over base. And we set up the reaction table, the acid dissociation reaction table, and find the change, the equilibrium concentration, and we found that if the acid is a weak acid, when Ka is very small, then the concentration ratio, acid-base, can use the initial concentration, acid and the base ratio. Okay, it's approximate by initial concentrations. And when hydroxide is added, sodium hydroxide is added, it undergoes acid-base neutralization. It reacts with the acid in the buffer solution, will decrease the initial concentration of acid and increase the concentration of the base, conjugate base. And so we, in this case, we set up a reaction table for this neutralization reaction. Okay, we calculate how much weak acid decrease, how much concentration of the conjugate base increase, and then use that final concentration of the acid and the base after neutralization reaction as initial concentration to set up another table, the acid dissociation reaction table, and then calculate the ratio of hydronium or of the acid, okay, and the base, and then calculate the pH for the buffer solution. And we found the pH slightly increased compared to the buffer solution. Okay, the change is very small. Now, when the acid is added, the reaction of the acid undergo neutralization reaction with the base in the solution. Okay, and similar to hydroxide, adding hydroxide, we set up a reaction table, this neutralization reaction table, and find the change of acid increase, base decrease. We find the final concentration of the weak acid and conjugate base after neutralization, and use them as initial concentration. Set up another table for acid dissociation reaction and find the ratio of the acid over base, and then calculate the pH, which decreases slightly. We already know that for a buffer solution, the hydronium ion concentration is determined by the ratio of the weak acid and the conjugate base. Now let's derive the equation. So we first write the Ka, the rate acid constant, which is the hydronium ion multiplied by the base, conjugate base, divided by the acid. Okay. Now in this equation, hydronium ion is here. In order to calculate hydronium ion concentration, we modify this equation. So hydronium ion will be Ka multiplied by the acid and divided by the base. Okay, so that's why this equation shows hydronium ion concentration is proportional to the ratio of acid over base. And we have seen this equation many times. Okay, Ka times acid over base. Okay, now let's apply negative log on both sides. And so negative log on both sides, and the left side, negative log hydrogen ion is just this is just the pH, the definition of pH. Okay, pH is defined as negative log hydrogen ion. Now what about the right side? Right side is negative log Ka times the ratio of acid over base. Now if we have a log, two numbers multiply each other, this can written as log A plus log B. And therefore the right side is negative log Ka minus log the ratio of acid over base, because we separate this product, okay, like here, into the summation of two logs. Okay, now negative log Ka is just pKa. Okay, the definition of pKa, just like pH is pKa. So we have this equation, pH is pKa. Now the last term, negative log acid over base, we can write as so when you have a log, let's say a n, okay, n log a is log a to the nth power. So this can be written as log a acid over base, okay, to the -1 power, because here you have a negative sign. It's a power just like n here. So you go to nth power. Now negative some, if 3 to the -1 equals 1 over 3, so it's the inverse. And therefore, instead of acid over base, here you can write as base over acid, but in front of the log is positive. So pH equals pKa plus log base over acid. Okay, it's important to remember that when you calculate the hydrogen ion, you use the ratio of acid over base. But when you calculate the pH value, it's pKa plus log base over acid. Okay, this equation is called Henderson-Hasselbalch equation. Okay, this equation allows you to calculate the pH if you know the ratio of acid and the conjugate base in the buffer solution. On the other hand, if you want to make a buffer solution with a desired pH value, for example 4.5, then you can calculate what is the ratio you need, the acid and the base ratio, or base over acid ratio, and then you can calculate how much acid, how much base you needed in the solution to make the buffer solution. One more thing I want to point out is that in this Henderson-Hasselbalch equation, both concentration of the base and the acids refer to the equilibrium concentration. Suppose we add 0.5 molarity of the weak acid, 0.6 molarity of the conjugate base, and make a buffer solution. Strictly speaking, we cannot use these numbers to put into this equation because they are not equilibrium concentration. We need to set up a table and find the change and the equilibrium concentration. However, as we shown in previous slides, the problem 19.1, if Ka is small, then the change X is small, so this initial concentration is approximately just the equilibrium concentration, and therefore we can, in this equation, the Henderson-Hasselbalch equation, we can assume these are just the initial concentration. So whatever you added is this concentration. So base is 0.6 and acid is 0.5, and then you can calculate pH for the buffer solution. Now you can try to use this equation and go back to the sample problem 19.1, and instead of using all those tables, just use this equation and use the initial concentration calculate, and you will find you get the same answer. The buffer capacity is a measure of the strength of the buffer, or its ability to maintain the pH following addition of strong acid or base. There are mainly two factors. One is the concentration. The greater the concentration of a buffer components, the greater its capacity to resist the pH change. Now let's compare two solutions, buffer solution. One contains acid, weak acid 0.5 molarity. Another one, the conjugate base is also 0.5 molarity. Another buffer solution contains conjugate acid, the acid 0.1 molarity, and the conjugate base also 0.1 molarity. Now, which one has a greater capacity? Well, first one, okay, because they have a higher concentration of acid and the conjugate base. And if you have higher concentration, then the solution, buffer solution, can absorb more added acid or base and maintains a constant pH value. Okay, so that's the first factor. The second one is how close the two components are to each other. All right, the acid and the conjugate base. So let's also compare two solutions. And this is one, okay, we have both acid conjugate base 0.5. And let's have another one which have acid also 0.5. And the base, okay, base which is different 0.5. So maybe let's say 0.3. Or it can be 0.7. As long as these two are different, okay, then this capacity is lower and this is higher capacity. Okay, now this is because if you remember, the pH value is determined, actually calculated by pKa plus log base divided by acid, okay, HA, okay, or anion. So anion here. So it's the base divided by acid. It's the ratio of the base divided by acid. If the ratio, if these two are the same, okay, then whenever you add small amount of acid or base, the ratio change is much smaller than when they are different. In the textbook, there are two examples showing you that when the concentration of acid and conjugate base are the same, it resists most change of the acid or base added for the pH value. This diagram shows the relation between buffer capacity and the pH change for 4 solutions. Initially, these 4 buffer solutions are all have pH value 4.74. Okay, when a strong base is added to these solutions, the most concentrated one change the least. Okay, so it changed to about still 4.76, for example, right here. Okay, now when you decrease the concentration of the buffer, the range increase, the change increase when as base is added. For the least concentrated one, 0.03 concentration of the buffer solution, the pH value changed the most from 4.74 to 5.05. The buffer range is the pH range over which the buffer is effective. The buffer range is also related to the ratio of buffer component concentrations. The closer the acid to the base, or the ratio is closer to 1, the more effective the buffer. If one component is more than 10 times of the other, then the action is poor. Buffering action is poor. Now pH is calculated by pKa plus log base divided by acid. Okay, so if B is 10 times of A, then log 10 is 1. So pH is pKa plus 1. Now if acid is 10 times of B, then the log ratio is log 1 divided by 10 is negative 1. So pH is pKa minus 1. And therefore, buffers have usable range, okay, within positive negative pH unit of pKa. It's pKa plus or minus 1. Sample problem 19.2. The molecular scenes below represent samples of 4 weak acid conjugate base buffers. The acid is blue and green. So here is one, and the anion is green. So this is a anion, and this is acid. And other ions water are not shown. So question is, which buffer has the highest pH? Now to find the pH, we need the ratio of base over acid. Okay, and since the volume of all the samples are the same, and therefore all we need is to count the particles of each species present in each scene, and that will represent the molarities, and then we calculate the ratio of the base over acid. Let's count the acid and the conjugate base in each scene. So for scene A, we have 1, 2, 3. We have 3 acid, and we have 1, 2, 3, and 3 conjugate base. In scene 2, we have 1, 2, 3, 4. We have 4 acid and 2 bases. And similarly, we can find in scene 3, we have 1, 2, 3, 4. That's the acids, and the base 1, 2, 3, 4. The last one, 1, 2, so 2 acid and 4 bases. Okay, so these represents the concentration because volume are the same. So we calculate the ratio. Now remember, pH equals pKa plus log base divided by acid. So we use base divided by acid. Okay, and for the first one, the ratio is 1. For the second one, 2 divided by 4 is 0.5. Third one is 1. Last one, 4 divided by 2 is 2. Okay, so the highest pH is the highest base divided by acid ratio, and that's the number 4. So the answer is sample 4 has the highest pH value. Question B. Which buffer has the greatest capacity? The buffer capacity is determined by 2 factors. One is the concentration. The more concentrate, the greater the capacity. And the other one is the concentration of acid and the conjugate base should be close, very close. The ratio should be close to 1. So if we look at sample 1, the ratio is 1. Sample 3, ratio is also 1. Okay, so both has ratio 1. All right. Then we look at which one has higher concentration. Now in number 3, sample 3, the concentration, acid, and the base and acid both are 4. In sample 1, both acid and conjugate base concentration are 3, and therefore sample 3 is more concentrated, and therefore the answer is sample 3 has the greatest buffer capacity. Okay, last question is, should we add a small amount of concentrated strong acid or strong base to convert sample 1 is this one, to sample 2. Okay, so if we look at the ratio, sample 1 ratio is 1, sample 2 ratio is 0.5, and the pH is related to the ratio. Okay, ratio base divided by acid. A smaller the ratio means a smaller pH. A smaller pH means you need more acidic, and therefore we need to add a strong acid to convert sample 1 to sample 2 so that it will decrease the pH value. In order to make a buffer solution, first we need to choose the conjugate acid-base pair. So how do we do that? Well, look at this equation. The pH of the buffer solution is pKa of the weak acid plus log the base concentration divided by acid concentration. And we also know that the best buffer is when the concentration of base and acid are close to each other. So the ratio is approximately 1. And that means pH, as we already mentioned before, is pKa of the weak acid plus minus 1. That's the range of pH. And therefore, the pKa, this pKa should be close to the desired pH value. So, for example, if we want pH of a buffer solution 4.6, okay, a good acid-base pair should be acetic acid and its conjugate base, so acidic anion. Okay, why? Because the pKa of this acid is 4.76, so this pKa is very close to the desired pH. Okay, and so that's the first one. Choose the conjugate acid-base pair, and then we need to decide the ratio of the acid and the conjugate base. Using this equation, we can calculate. Okay, after we calculate the ratio, then we determine the buffer concentration and calculate the required volume of stock solution and masses of components. And finally, mix the solution and correct the pH. Sample problem 19.3. An environmental chemist needs a carbonate buffer pH 10. Okay, that's the desired pH for the buffer solution. The question is, how many grams of sodium carbonate must she add to 1.5 liter of freshly prepared 0.2 molarity sodium bicarbonate to make the buffer solution? So first, which one is acid, which one is conjugate base? If we compare these two molecules, you will see that sodium bicarbonate has an extra hydrogen, and so that indicates this is acid, okay, which can donate the proton. So it's acid. After donate the proton, you get this conjugate base. So sodium carbonate is the base. Okay, so we know that the pH of this solution can be calculated by pH, which equals pKa plus log base over acid. And in this question, pH is given, it's 10. pKa is also given here, the acid. pKa, acid constant is given. And the concentration of the weak acid, sodium bicarbonate, is 0.2. And the question is, how many grams of carbonate? Well, using this equation, we can first solve the concentration of carbonate ion, okay, with the concentration solved, and also the volume is given, so we can calculate the number of moles. So first, you calculate the concentration. So concentration of carbonate And then from concentration, we calculate the number of moles. And from number of moles, you calculate grams by molar mass. So let's first calculate the ratio of base over acid. Okay, here is the equation again, and we know the pH. We need the pKa. We know Ka. So Ka needs to be converted to pKa, negative log Ka, and that gives you 10.33. Okay, so plug in everything. So this is the pH, this is the pKa, so the ratio can be calculated. Okay, so ratio is 0.47, and then acid is given, so we can solve. The base is the acid concentration times the ratio, and that gives you 0.094. So we have the base concentration and we have the volume, so volume times the concentration, that gives you number of moles, and this is the number of moles for carbonate that is needed. Okay, and with number of moles, then we can calculate the mass. So the mass is number of moles times molar mass, and the answer is 15 grams of the sodium carbonate. In the last step, to calculate the mass of sodium carbonate, we need to use the molar mass of sodium carbonate, not the mass of carbonate. So from the equation, what we solved is the concentration of the carbonate. Okay, but the carbonate concentration should equal to sodium carbonate. Okay, so one carbonate forms one sodium carbonate, so they have equal concentration, molarity, and therefore the number of moles of carbonate, which 0.14, also equals the number of moles of sodium carbonate. So using this number of moles of sodium carbonate, you need to multiply by the sodium carbonate molar mass, and this gives you grams of sodium carbonate. We now move to another topic, acid-base titration. The purpose of titration is to find the concentration of an acid or a base. The concentration of an acid is determined by neutralization of the acid with a solution of base of a known concentration. The concentration of a base is determined by neutralizing the base with an acid. There are two important concepts in neutralization. One is equivalence point. The other is the end point. The equivalence point of the reaction occurs when the number of moles of hydroxide added equal to the number of moles of hydrogen ions originally present, or vice versa. The end point occurs when the indicator changes color. End point is not always same as equivalence point. However, the indicator should be selected so that its color change occur at the pH close to that of equivalence point. Here shows a titration curve for a strong acid, strong base titration. It is a titration of hydrochloric acid with sodium hydroxide, and this curve is based on the data shown on the left side. At the beginning, when no sodium hydroxide is added, pH of the solution is 1.0, and this is also shown the first point on the titration curve. Okay, a low pH indicates a acidic solution, and you can also see in the molecular scene there are two hydrogen ions in the solution, okay, indicating it's a acidic solution. When sodium hydroxide is added, 10 milliliter sodium hydroxide, pH increase to 1.22. Okay, more sodium hydroxide added, the pH increase gradually. Okay, you can also see in the titration curve, more volume of sodium hydroxide is added, pH of the solution increase slowly. Okay, and this is because the sodium hydroxide added will react with the hydronium ion, consumes hydronium ion in the solution. So if you look at the molecular scene, 2 hydronium becomes 1, and the other one becomes a water molecule. So hydronium ion concentration decrease when more sodium hydroxide is added, but it's still an acidic solution because you still have hydronium ions in the solution. So the pH is still less than 7. Okay, it increases slowly until the volume of sodium hydroxide added approach 40. Okay, for example 39. Then you can see pH start to jump. Okay, when the sodium hydroxide volume equals 40, okay, if you look at the data, the pH becomes 7, and this is called equivalence point. At this point, the added hydroxide concentration equals the hydronium in the solution. In other words, all the hydronium ion in the original acid solution are consumed by hydroxide added. So now the solution becomes neutral, okay, and the pH becomes 7, and this is an equivalence point. When more sodium hydroxide volume, okay, is added, the pH of the solution continue to increase until it becomes very high, okay, above 12, and then it start to increase slowly, okay. And if you look at the molecular scene, only hydroxide exists in the solution, and this is becomes a basic solution. The equivalence point is the most important point on the titration curve. Knowing the volume of sodium hydroxide added corresponding to this equivalence point allow us to calculate the number of moles of sodium hydroxide which equal to the number of moles of hydrochloric acid, so we can calculate the concentration of sodium hydrochloric acid solution. But how do we find the equivalence point? We add an indicator, a chemical that changes color at the equivalence point. Ideally, we want an indicator that changes color exactly at this equivalence point. In reality, indicators may change color at a different pH. For example, phenolphthalein change color from 8 to 10. Okay. However, you can see on the titration curve, here is called the vertical portion. Okay, and within this vertical portion, a small volume of sodium hydroxide causes a significant jump of pH. In fact, 1 drop of sodium hydroxide added to the solution may change pH from 4 to 11. A huge change, just 1 drop of sodium hydroxide. And therefore, as long as the color change of a indicator is within this range, this vertical range, then they should give you an accurate indication of equivalence point. In the following, we are going to show some equations to calculate the pH during strong acid, strong base titration. For example, we add hydroxide into a strong acid, okay, and then calculate the pH. So before we do the titration, before hydroxide is added, since it's a strong acid, all the acid becomes hydronium ion. So the hydronium ion concentration is just the concentration of the acid, and the pH is the negative log of hydronium ion. Okay, so that's the initial pH before hydroxide is added. Now when the hydroxide is added to the solution, but before the equivalence point is when hydroxide equals to hydrogen ion. But before this point, that means hydroxide is less than hydrogen ion. So the solution is still acidic. Okay, in order to calculate the pH value, we need to know how much hydrogen ion left after it reacts with hydroxide. So we calculate initial hydrogen concentration or number of moles. Okay, the moles of hydrogen ion in total amount hydrogen ion in the solution, which is the number of it's the volume times molarity of the acid, and then hydroxide added number of moles is the volume of the base times molarity of the base. So the number of moles hydrogen ion remaining in the solution after reaction is the number of moles. It's this one. Number of moles hydrogen ion minus the number of moles of hydroxide. Okay, so we get the number of moles hydrogen ion in the solution, and then you divide by the total number of volume, give you concentration of hydrogen ion after hydroxide is added. Okay, and then your pH can be calculated. It's negative log hydrogen ion concentration. So any point before equivalence point, the pH can be calculated as long as you know how much volume of base is added. When the reaction reaches the equivalence point, the hydrogen ion equals hydroxide. pH is 7. Without calculation, we know pH is 7. Now, after the equivalence point, now we know hydroxide is greater than hydrogen ion. So we have to find out how much hydroxide in excess, okay? And then we can calculate hydrogen ion in the solution. So to calculate the excess amount of hydroxide, again, we need to know the initial number of moles of hydrogen ion, how much hydroxide added, the number of moles, but this time we use number of moles of hydroxide minus hydrogen ion, and that gives you excess amount of hydroxide. Okay, and then we can calculate the concentration of hydroxide just like we did for hydrogen ion. Okay, after we get hydroxide, okay, we can either calculate the pOH and then calculate the pH, use 14 minus pOH, or we can use hydroxide times hydrogen ion equals 10 to the minus 14. So use this equation, we can also calculate hydrogen ion concentration and then calculate the pH. Let's look at an example. In this example, we use 0.1 molarity of sodium hydroxide to titrate 40 milliliter 0.1 molarity of hydrochloric acid. Okay. Now, before we add the sodium hydroxide, the solution contains a strong acid, so the hydrogen ion just equal to this acid concentration, which is 0.1. That's the hydrogen ion concentration. So pH can be easily calculated to be 1. All right, it's an acid solution. Okay. Now, when we add the sodium hydroxide, some of the hydrogen ion may be reacted. So let's say we add 20 milliliter of sodium hydroxide. So what will be the pH value? Okay, to calculate pH, we need to know the hydrogen ion concentration. So let's calculate what is the total hydrogen ion number of moles. Okay, so the total number of moles of hydrogen ion is the volume, which is 40 milliliter. We need to convert to liter, 0.04, times concentration, 0.1 molarity. Molarity means moles per liter. Okay, when we write it as this way, we can cancel the volume, liter, we get the number of moles. So that gives you 4 times 10 to the minus 3 moles of hydrogen ion. So that's how many number of moles hydrogen ion in the solution. Now, how many number of moles of hydroxide added is the volume is 20 milliliter, okay, which is 0.02 times 0.1 molarity. Again, use this as a conversion factor, we get number of moles. Now compare these two number of moles, we can see hydrogen ion is in excess amount. All the hydroxide added 20 milliliter is reacted. Okay, they all reacted. So we have excess amount of hydrogen ion. In other words, this is before equivalence point. Okay, in fact, because they have the same concentration, we would expect the equivalence point will be when the volume hydroxide also equal to 40 milliliter as the acid. Okay, so before equivalence point, it's acidic solution. We need to calculate the hydrogen ion concentration. We calculate the remaining hydrogen ion after reaction. So the number of moles can be calculated by the moles before the total moles of hydrogen ion minus the number of moles of hydroxide added. Okay, that's the number of moles. And then we divide by volume to calculate concentration. And note that the volume now is the sum of the volume of acid and the base added. That's the total volume. And so that gives you 0.03333 molarity. With this excess amount of hydrogen ion, we can calculate the pH value, which is 1.48. Okay, so you see the pH value change from 1 to slightly to 1.48 before the equivalence point. So any point before equivalence point, the calculation follows this procedure. You need to calculate excess amount of hydrogen ion. Okay, number of moles first, and then concentration, and then you can calculate the pH. As I explained in the last slide, for this acid solution, we need 40 milliliter of sodium hydroxide to reach the equivalence point. And at this point, the pH should be 7 because it's a neutral solution. Okay, what if we add sodium hydroxide more than 40 milliliter? For example, 50 milliliter, and that's the after equivalence point. So how do we calculate the pH? Well, after excess amount of sodium hydroxide added, we need to know what is the hydroxide in the solution. Okay, so we calculate first number of moles of hydroxide added, which is the volume times concentration. So this is the moles, and we already calculated the moles of hydrogen ion. So use hydroxide added minus hydrogen ion give you excess amount number of moles of hydroxide. To calculate the concentration, we use moles divided by volume, and the volume is the volume of the acid plus the base of the volume added, total volume. And this is excess amount of hydroxide concentration. So we can calculate the pOH, and then we can calculate the pH. So pH is 12, and that's a basic solution, indicating it's after the equivalence point. So any point after equivalence point follows this calculation procedure. We need to calculate excess amount of hydroxide. First, the number of moles, and then the concentration, and then we can calculate the pH. Here shows the curve for a weak acid, a strong base titration. For example, strong base may be sodium hydroxide, and weak acid may be propanoic acid. Okay, so we add hydroxide into propanoic acid to titrate the solution. And for comparison purpose, we add a dotted line to show strong acid, strong base titration curve that you already seen. All right. So if you compare these two, you will see some similarities and some differences. Okay. So first is the initial pH value for weak acid solution is higher than the strong acid solution, because weak acid only certain amount of the molecule dissociate becomes hydrogen ion. So the hydrogen ion concentration is lower. In weak acid solution, pH is higher. So you start with a higher pH value. And second, the curve rises gradually in the so-called buffer region. So this is a buffer region And this is because when you add sodium hydroxide to propanoic acid, okay, you make water plus sodium propanate. And sodium propanate is the conjugate base of this acid. So in this region, you have a mixture of weak acid and its conjugate base, and that's the buffer solution. And so in this buffer solution, a buffer region, the pH value rise very slowly. Okay, so that's the second feature of this curve. And the third feature is that the pH value at the equivalence point is not 7. In fact, here is 8.8, okay, close to 9. And this is because at the equivalence point, we have equal amount of acid and base. So these two are the same. Okay, so you get 100% sodium propanate. However, sodium propanate is a salt that is not neutral, because this salt, sodium, comes from strong base. Propanate comes as a weak acid. So this salt expect to be basic, and therefore the pH value is higher than 7. So in this case, it's 8.8. You can calculate the pH by using pKa of this salt. Okay, we have learned how to calculate the pH for the salt. Okay, so that's the third feature, and then the pH increases slowly beyond the equivalence point. We have shown before that the indicator phenolphthalein changes color from pH 8 to 10. And for strong acid, strong base, the equivalence point pH is 7. So the end point doesn't match exactly for equivalence point. However, for weak acid, strong base, the equivalence point pH is above 7. In this case, is right inside the color change for phenolphthalein. So in this case, the end point matches equivalence point very well. In the following, I'm going to go over the steps to calculate the pH for a weak acid strong base titration. And you will see that the calculation is much more complicated. First, let's look at the initial pH before hydroxide is added. So this is for a weak acid. Now for strong acid, hydronium ion equal to the molarity of the strong acid. So the calculation is much simpler. But here, because it's weak acid, only small amount of molecule dissociate. So usually we need to list a reaction table to find how much dissociated and what's equilibrium concentration. However, if the acid is weak, Ka is a small number, then we already showed that this is the equation to calculate hydronium ion concentration, and that is the square root the Ka acid constant times initial acid concentration. So you see this is a useful equation to remember for a weak acid, okay, to calculate the hydronium concentration. So it's a square root initial concentration times Ka, and then pH can be calculated. So that's for initial pH. After hydroxide is added, okay, so here after hydroxide is added, but before equivalence point, how do you calculate pH? Now, if it's a strong acid, strong base, we calculate the number of moles, total number of moles hydronium ion, and then minus the number of moles hydroxide. Okay, and then you can calculate concentration of hydronium ion remaining in the solution. So that's for strong acid, strong base. For a weak acid, weak base, the problem is hydronium ion is not clear because only part of it dissociate. Okay, so how do we do that? Well, we realize that whenever the hydroxide is added to the solution, it reacts with the acid to form a conjugate base, okay, plus water. So before equivalence point, we have a mixture of acid and conjugate base, and that's the buffer region, Okay, and we already learned the equation to calculate hydrogen ion in a buffer solution, okay, or acid conjugate base pair is directly related to the ratio of the acid over base. It's the Ka times acid divided by base. Okay, so I hope you still remember for a buffer solution, hydrogen ion is Ka times acid divided by base. Okay, so that's the equation to calculate hydrogen ion, and the pH is calculated by pKa plus log base divided by acid. Again, I hope you still remember this equation. So that's the equations to calculate the pH before equivalence point. Okay, so that's the before equivalence point. How do you calculate the pH value at the equivalence point? Well, if it's a strong acid, strong base titration, pH is 7, and no calculation is necessary. But for a weak acid, strong base titration, the calculation is much more complicated at the equivalence point. And this is because when you have same amount of acid and sodium hydroxide for the titration at the equivalence point, they have same amount, which gives you water plus the salt, sodium salt. And this salt is not neutral because the anion comes from a weak acid. This is a weak acid, so you expect the salt to be basic. Okay, pH is more than 7, and this is because the anion undergo hydration reaction. This is the hydration reaction. It reacts with water to go back to the weak acid. At the same time, generate hydroxide, make solution basic. So how do you calculate the hydroxide concentration in this weak basic solution? Well, similar to the acidic weak acid, the hydrogen ion concentration is calculated by this equation, the square root Kb times the anion, the base, weak base. This is a conjugate base of the acid. Okay, so again, I hope you still remember for a weak base, the hydroxide is calculated by square root Kb times the base concentration. Okay, so with this hydroxide calculated, then you can calculate the hydrogen ion, which is Kw divided by this hydroxide, and then you can calculate the pH. But before you calculate hydrogen ion, you need to calculate the concentration of the anion, the base, because this base concentration needs to be calculated. When you add the base, the total volume change. So you need to calculate, use the number of moles divided by total volume. Okay. Also, what is Kb? Is the base constant for the conjugate base anion, the Kb. Now, usually we know Ka for the acid, weak acid. So you use Kw divided by Ka, give you Kb. Okay. So essentially, at the equivalence point, we are calculating the pH for the salt. This is about the salt that generated due to the weak acid strong base titration at the equivalence point. Okay, so after the equivalence point, then you have extra amount of hydroxide. And so first you calculate the concentration. Again, you need the number of moles of hydroxide in excess divided by the total volume, give you concentration. With hydroxide, excess amount of hydroxide concentration, then you can calculate the hydrogen ion concentration. Is Kw divided by hydroxide. Then you can calculate the pH. Sample problem 19.4. Calculate the pH during titration of 40 ml of 0.1 molarity propanoic acid. The Ka is 1.3 times 10 to the minus 5. So that indicates it's a weak acid. Okay, and weak acid, after adding the following volumes of 0.1 molarity of sodium hydroxide. So it's a titration of weak acid strong base. And because they have same molarity, 0.1, 0.1, so we would expect the equivalence point will be reached when volume is the same, 40 milliliter. So here is the 40 milliliter. So C should be the equivalence point, and this A is the initial pH, B is the pH before equivalence, C is the equivalence point, D is after equivalence point. Okay, so we'll follow the steps we already talked about in the last slide. So first, let's calculate before hydroxide is added, the initial pH. Now it's a weak acid, and usually you list a table to calculate the hydronium ion, but we already have the equation. That is, hydronium ion is square root Ka times the acid concentration. So acid concentration is 0.1, Ka is given, so you can calculate hydronium ion, and then pH can be calculated. So that's answer A. Now let's look at B. When 30 milliliter of sodium hydroxide is added to the weak acid, propanoic acid, what is the pH value? Well, first we need to know that when sodium hydroxide is added to the weak acid, the conjugate base is formed. So it's a mixture of acid and conjugate base. And so to calculate the pH, we should use this equation. pH pKa plus log acid, weak acid is conjugate base. So weak acid in this case is the propanoic acid, and the conjugate base is propanate, the anion. Okay, so this is due to the reaction acid plus sodium hydroxide added give you the anion plus water. Okay, so therefore, in order to use this equation, we need to know how much acid remains in the solution, how much base generated by the titration reaction. So to calculate the concentrations, we first calculate the number of moles. The total number of moles of acid is the volume 0.04 given here, 40 milliliter, times molarity. So that's the number of moles for acid, and the sodium hydroxide is the volume 30 milliliter times 0.1 molarity, and give you number of moles of hydroxide added. And you can see the acid is in excess amount. So you have excess amount. So how much in excess? You can simply use 4 minus 3, give you 1 times 10 to the minus 3 moles. Okay, that's the acid remains in the solution. But don't forget, during the reaction, it produces the base, the conjugate base. So how much it generate? Well, since this all reacted, the hydroxide all reacted, so you would expect the same amount, 3 times 10 to the minus 3 base is generated here. Okay, moles, okay, is generated. All right, and then you divide by volume. So that's one way we can calculate the acid moles, acid and the base, and then calculate the concentration. But a better way, okay, is to write the reaction table. And this reaction is between the weak acid and the hydroxide. It's a neutralization reaction, give water and the conjugate base. Okay, so this is a better way to do it without confusion. So acid, weak acid, conjugate base. So initially we have 0.04 acid, and we add this amount of hydroxide, and initially there's no conjugate base. Okay, and then because hydroxide is a small amount and acid is in excess amount, so hydroxide should all react. So the react concentration should be 0.003. Okay, so reactants negative, products positive, and therefore at equilibrium we get the conjugate base is 0.003, and at equilibrium acid remains is also 0.001. So it's same as our calculation here, but this method is more clear. Okay, it's more it's preferred method. So with these numbers, okay, we can calculate the volume or calculate the concentration, and then plug in this equation. Okay, so this equation pH equals pKa plus log base divided by acid. Since they have the same volume, so if you divide by the same volume and then you calculate the ratio, the volume cancel each other. So in this equation, you don't have to divide by volume first. You just use the moles of the base. So base is the moles here, acid is moles here. Okay, and the pH is 5.37. Okay, let's now look at the C. 40 milliliter of sodium hydroxide has been added. What is the pH? We already know that when 40 milliliter of sodium hydroxide is added, the number of moles of sodium hydroxide equal to the number of moles of propanoic acid, and therefore it's the equivalence point, and they all become salt. That's the sodium propanate salt. Okay, so essentially we want to calculate pH of this salt. Okay, now to verify this conclusion, let's draw the reaction table, which is between the weak acid and the hydroxide. Neutralization give you water and the conjugate base, which is the salt. Conjugate base combined with sodium, that's the salt. Okay, so initially we have 0.004 moles of acid, and the base we add the same amount because 40 milliliter times 0.1, so that's the same amount, and the reactant must be also the same because reactants both has 0.004, so that's the reactant. Reactants are negative, products are positive. So at the equilibrium, then all acid is reacted, 0 remaining. Hydroxide also all reacted, and the product is formed 0.004 moles of propanate anion. And because this anion is a weak base, and so it will react with water to generate hydroxide. So in order to calculate the hydronium ion, we need to set up the reaction table to calculate hydroxide concentration. Now, before we do that, we need to calculate the concentration. This is number of moles. So number of moles divided by the total volume, which is the volume of the acid plus volume of the base, the hydroxide. So this is the concentration of propanate anion in the solution. And so next we are going to set up the table, calculate the hydroxide concentration, and then we can calculate the hydronium ion concentration. At the equivalence point, the solution is basic because the salt contains the anion that react with water, go back to the weak acid and generate hydroxide. So here propanate anion is a base, is a weak base, and for weak base we already have an equation to calculate hydroxide, and that is the square root Kb times concentration of the base. Now if you forget this equation, okay, and we can just derive this equation here. So we draw the reaction table, the initial concentration 0.05 just calculated in the last slide, and change x and the final equation concentration. So to solve x, we need to know Kb because this is the base dissociation reaction. Kb can be calculated by Kw divided by Ka. Ka is given for the propanoic acid. Okay, so that gives you Kb 7.7 times 10 to the minus 10, and then use the Kb we solve x. So Kb equals x squared. So x times x divided by the base, and since Kb is so small, 10 to the minus 10, x must be very small. So we can omit x. So x squared divided by 0.05 equals Kb. So this is Kb, and this is the initial concentration of propanoic acid. Okay, and therefore using this equation we can derive x. which is the hydroxide concentration, is square root Kb times base concentration, and plug in the data, and we get 6.2 times 10 to the minus 6. With hydroxide, we then calculate the hydronium ion, which is Kw divided by OH, and then we calculate the pH, which is 8.8, indicating solution is basic. Indeed, when 50 milliliter of sodium hydroxide has been added, what is the pH? Well, 50 milliliter is more than 40 milliliter, so it's past the equivalence point, and there are excess amount of sodium hydroxide in the solution. So we need to calculate what is the excess amount of sodium hydroxide. So first we calculate the added sodium hydroxide. So hydroxide number of moles equals the volume times molarity, and give you number of moles, and then use this moles minus the number of moles of initial acid concentration, or number of moles. So give you 0.001 moles, and that's the excess number of moles of hydroxide in the solution. Then use this number of moles divided by total volume, which is 0.09, give you the concentration of hydroxide in the solution, okay, after 50 milliliter of sodium hydroxide added to the solution. And you still have this concentration left unreacted. And then we calculate hydronium ion, and then calculate the pH, which is 12.05. How does the titration curve for a weak base strong acid titration look like? For example, we add hydrochloric acid, which is strong acid, to ammonia solution, which is a weak base. And because it's a base, so the beginning, the pH should be greater than 7. And because it's a weak base, so the pH should be lower than strong base. And here is a titration curve. At the beginning, the pH is 11, and that's corresponding to the ammonium solution. When hydrochloric acid is added, so when you increase the volume, hydrochloric acid, the pH value decreases slowly and entering into buffer region, just like the weak acid strong base titration. So here, ammonia react with hydrochloric acid to form ammonium chloride. And the ammonium chloride, so ammonium ion is a conjugate acid of ammonia. So this is acid, conjugate acid of the weak base. So in the solution, there's a mixture of ammonia, weak base, and the conjugate acid, ammonium, and therefore it's a buffer region, and the pH decrease gradually in this region. Okay. Another important feature is the equivalent point. The equivalent point pH is less than 7, and this is because at the equivalent point, all ammonia hydrochloric acid react to form the salt ammonium chloride. But the ammonium chloride is not a neutral salt. This salt is actually acidic because ammonium ion react with water, go back to ammonia, and also at the same time it generate hydronium ion. Okay, that makes solution acidic, and therefore the pH value is lower than 7. In this case is 5.27. Okay, now remember, for strong acid, strong base titration, the equivalence point is 7. pH is exactly 7 for strong acid, strong base. For weak acid, strong base titration, we already shown before, the pH value is greater than 7. Okay, one example we showed is pH is 8.8. Okay, so that's for weak acid, strong base titration. If it's a weak base, strong acid, then the pH at the equivalence point is actually lower than 7, and in this case 5.27. And a good indicator is methyl red, have a color change from pH about 3 to pH about 7. An acid-base indicator is a weak organic acid whose color differs from that of its conjugate base. Let's use phenolphthalein as an example. In acidic condition, when there are enough hydrogen ions, phenolphthalein takes the left side form. So this is the phenolphthalein in acidic condition. And note that the molecule has 2 hydrogens to donate, 2 protons to donate, and therefore it's a weak acid. Okay. Now this molecule is colorless, no color. When base is added to the solution, base will deprotonate one of the hydrogen from the molecule, and the molecule rearranged becomes the right side form. And this right side form is the conjugate base of the weak acid. And this conjugate base is pink color. So the phenolphthalein may be different color depends on the hydrogen ion. If there are enough hydrogen ion, it takes left side form, it's colorless. If the solution has enough hydroxide, very little hydrogen ion, it takes to the right side form and becomes pink. And therefore, this molecule can be used to monitor the pH change during the acid-base titration. The color of an indicator changes over a specific narrow pH range, a range of about 2 pH units. This diagram shows the colors and approximate pH range of some common acid-base indicators. For example, phenolphthalein. The color change between here is 8 and here is 10. So between 8 and 10. So below 8, the color is the phenolphthalein is colorless. Above 10, it is pink. Methyl red, on the other hand, is red color when the pH is below about 4.2 and becomes yellow when the pH is above 6.2. Another example is bromothiamine blue. The color is yellow when the pH is below 6 and becomes blue when the color is above 7.6. And here shows 3 solutions of this indicator. And when the pH is less than 6, it appears yellow. And here shows the pH is above 7.6, which is blue color. In between, the color depends on the pH value. How do you choose an indicator for a particular acid-base titration? A indicator should be chosen so its color changes occurs at the vertical portion of the titration curve. For example, the first titration curve involves strong acid, strong base. How can you tell? Well, first is the pH value at the equivalence point is 7, and that is an indication it's a strong acid, strong base titration. Also, at the beginning, the pH is very low. That's a strong acid. And at the end, the pH is very high. So that's a strong base. Okay. For this titration, phenolphthalein, methyl red, both indicators are appropriate because they both are in the vertical region. Now, second curve is for weak acid, strong base titration. So how can you tell? Well, the pH at the equivalence point is above 7. In this case, is 8.8, and that's indication it's a weak acid, strong base titration. Another feature you can see is at the beginning, the pH is higher than strong acid, so it's a weak acid, strong base titration. Now for this titration curve, phenolphthalein is still good. It's at the vertical region, but the methyl red is not. And you can see to cause the color change, you need a large volume change from 10 to 45. That's a huge volume of sodium hydroxide need to be added to make the color change. Now the third curve is for weak base, strong acid titration curve. How do you know? Well, the equivalence point pH is below 7. It's 5.27. So that's indication weak base, strong acid titration. And also at the beginning, the pH is above 7, but not as high as strong base. And so again, it's a weak base, strong acid titration. For this titration, metal red is appropriate because it's at the vertical region, but phenolphthalein is not. Again, you need a large volume of hydrochloric acid to cause the color change for phenolphthalein. So it's not appropriate for the titration. Here shows a curve for the titration of a weak polyprotic acid. This titration curve looks like a combination of two titration curves. So let's separate into two of them. The left side is one titration curve. The right side is another one. And this is for sulfurous acid, which contains two hydrogens to react with hydroxide. So the left side is the titration of the first hydrogen to form hydrogen sulfide ion. Because hydrogen sulfide still has one hydrogen, so it's still acidic, and the equivalence point is at pH 4.25. And the second titration curve contains a second equivalence point which has a pH 9.86 because the formed ion is a sulfide ion, which is basic.